Good morning. Today we're going to talk about Math 101 and in particular Chapter 3, Section 2. All right, Chapter 3, Section 2 is formally entitled Solving Application Problems. And anytime we talk about applications in Math 101, usually we're talking about word problems. Solving let's see, the book actually says solving application problems. Let me fix it. Application problems. All right, here we go. Solving application. Really, I'm going to just subtitle that myself. I'm going to call it word problems. Story problems, number problems, all kinds of different names. All right, we're going to jump right in and do them. And folks, don't run away on this topic. It's not going to go away. The only way to get good at these is to practice them. So be sure to complete your assigned homework. Let's look at example 1 right in our text. Kind of a baby one. Let's see. Hang on, page 195. All right, please look along. Some of these problems are just a little too tedious to write out totally. Some of them go on for a couple paragraphs. So let's look at example 1, page 195, right at the bottom. Classically called a number type problem. It says 2 subtracted from 4 times the number is 10. Find the number. So 2... This is short enough, I can copy this one. 2 subtracted from 4 times a number is 10. Find the number. All right. The idea here is we translate the word is into an equals sign in setting up an equation. Typically we need two things to get started here. We need a let statement, and I suppose we're going to let x be the number of interest that we're supposed to find, and we need an equation. All right, so let me write that down. I'll say let x equal the number that we're looking for which we're looking. All right, so now we got to squeeze an equation out of this given information. 2 subtracted from 4 times the number is 10. All right, is 10, well, equals 10 then, right, because is means equals. 2 subtracted from 4 times a number. 2 subtracted from what? From 4 times a number. All right, so that wasn't too painful, and this is classically how we squeeze an equation out of the worded situations. So 4x minus 2 equals 10. Of course, we'll add 2 to both sides once we get the equation set up. So 4x equals 12. Divide both sides by 4. 4's cancel out on the left, and I'm left with x equals 12 fourths, which of course simplifies to x equals 3. All right, now the book makes a big deal about checking your answer. I'm not going to insist on it. Yes, again, the book makes a big deal about checking your answers. We don't insist that you check your answers. Maybe under duress on a test situation like that, you might want to consider checking your answer if you're a little bit shaky on it. All right, next we're going to talk about example 2 on page 196. Let me write that down. Example 2, page 196. And let's see. All right, it's another what they call a number type problem, so it's not too long, so I'm going to write it out. The sum of two numbers is 26. Okay. Find the two numbers if find the two numbers if the larger number is 2 less than 3 times the smaller number. And don't run away. Is 2 less than 3 times the smaller number. All right, so we're going to need two things. First thing is a let statement, and we've got two numbers involved here. It says the sum of two numbers is 26, and then it says two numbers if the larger number is less than 3 times the smaller number. All right, so one of these numbers is smaller than the other. One of these numbers is larger than the number, and it looks like the larger one is described in terms of the smaller one, right? It says the larger is, and it gives some characteristics, 2 less than 3 times the smaller. So I'm going to let x equal the smaller number, because then I can write an expression for the larger number. Well, the larger number is 2 less than 3 times the smaller. 2 less, 2 less. So that means I'll have 2 less, or minus 2, 2 less than 3 times the smaller. So the larger one is going to be 3x minus 2. So I now have an expression, two expressions for each of these numbers in terms of one variable, actually in terms of the smaller. So we now know that we can invoke this, the sum of two numbers is 26. So I'll simply take those two expressions for those two numbers. And I suppose I could get real fancy here, but I'm not going to. All right, I'll just write this first, the larger plus the smaller equals 26. Of course, I could combine like terms. 3x plus x is 4x. 4x minus 2 equals 26 then. Adding 2 to both sides, I'll get 4x equals 28. And if I divide then both sides by positive 4, the 4's cancel on the left, and I'll say x equals 28 fourths, x equals 7. All right. And have we answered the question? Let's check. Find the two numbers. Well, that's only one of them. So if x is 7, we have to find the other number, 3x minus 2. That's going to be 3 times 20. 3 times 7 is 21. 21 minus 2 is 19. So the two numbers of interest, we're looking for 7 and 19. Of course, we could check if we add these numbers. 7 plus 19 is indeed 26, and so that checks out, and 19 is 2 less than 3 times 7. All right, so 3x minus 2, 3 times 7 minus 2 indeed equals 19. So that checks out as well. Okay? Final answer, two numbers, 7 and 19. Okay? All right. I want to do number 5 from the homework list. Let me turn there. 3.2. Section 3.2, number 5 from the homework list. This is going to be on page 201. And let me write it down. Again, this is a short one. The sum of two consecutive integers is 87. Find the numbers. Let me write that out. The sum of two consecutive integers is 87. Find the numbers. All right, so I copied it from the book directly. Again, we need a let statement to begin with, and then an equation based on the given information. Two consecutive integers, the sum of two consecutive integers. Well, what I could do is say let x be the smaller of the two consecutive integers, and then x plus 1 is going to be the larger, right? If they're consecutive, one is smaller than the other, and of course, consecutive integers increase in breaks of 1. All right, so if x is the smaller, x plus 1 is the larger, so all we have to do then to set up an equation is say x plus 1 equals 87. The sum of these two integers is 87, and then grind out this rather simple equation. Combining like terms, I get 2x plus 1 equals 87. Subtracting 1 from both sides, I'll get 2x equals 86. Dividing both sides by 2, I'll get x equals 43. Now remember, 43 is our smaller integer, so that means our larger integer is going to be x plus 1, or 43 plus 1. That's going to be, of course, 44. So if x equals 43, x plus 1, the second larger integer, larger consecutive integer, is going to be 44. So my answer is 43 and 44. Those are the two numbers. All right, let's try another one similar to this, number 8 on the homework list. Again, this is number, all right. Number 8 on the homework list. This is on page 201. It says the sum of two consecutive even integers is 146. Let me write that down. The sum of two consecutive even integers is 146. And of course, similar to the last one, find the numbers. Or find the integers if you prefer. All right, similar to the last one, if I've got two consecutive even integers, well, one is bigger than the other and one is smaller than the other. So I'm going to say x equal the smaller of the two consecutive even integers. Now notice the word even here. Well, because these are even integers that are consecutive, even integers increase in breaks of 2, right? So not x plus 1, but x plus 2 is the next consecutive even integer, right? All right, so that's what's different about this one. So now I'll set it up similarly. The sum of these two consecutive even integers is 146, and this should be an easy enough equation to solve. 2x plus 2 equals 146, so 2x equals 144. So x, dividing both sides by 2, sorry about writing so low here, let me go up here. The 2's cancel on the left, x equals 144 over 2 is 72. So the second consecutive even integer is then going to be x plus 2, which is of course 74. So here's my final answer. Right? The two integers are 72 and 74. Not too bad, right? Let me get a fresh screen. Hang on. Delete, and add. All right. Scroll back up. All right, we're ready. let's look at example 3. Back to the examples, worked out examples in the textbook. This is example 3 on page 197. All right, now this one's too long to write out word for word, so I'm going to ask you to please turn to your texts and look on page 197, right at the top, example 3. Talks about 2006 Winter Olympics. In the 2006 Winter Olympics, Germany won the most medals and the United States won the second greatest number of medals. All right, now here's the money statement right here. Germany won 21 less than twice the number of medals won by the United States. All right, let me summarize this. I'll say Germany won the most medals. All right, U.S. won the second most. All right, and it tells us Germany won 21 less than twice the number of medals won by the United States. 21 less than twice the medals won by the U.S. All right, so I'm going to make a let statement here. Germany's medals are described in terms of the U.S. medals. So I'm going to say let X equal the number of U.S. medals won in those Olympics. All right, so then the number of German medals is going to be 21 less than twice the number of U.S. 21 less than twice the number of U.S. All right, so I can easily get a expression in X for the number of German medals. All right, so there's a let statement. Now we're going to set up our equation with this last bit of information in this problem. If the difference between the medals won by Germany and U.S. is 4, determine the number of medals won by Germany. All right, the difference between the number of medals is 4. All right, Germany and U.S. Let me write that down. Difference between German and U.S. medals is 4, and with that information they want us to determine the number of medals won by Germany. All right, well, Germany won the most medals, so what I'm going to do is take the German number of medals and subtract the U.S. number of medals, and I know that difference has to be 4. All right, I can solve this for X very easily. 2X minus X is just 1X. X minus 21 is 4. So if I add 21 to both sides, I'll get X equals 25. Now, X is the number of U.S. medals. We want to find the number of German medals. So we can find that easily now. If X equals 25, the number of U.S. medals, then 2X minus 21, that's going to be 2 times 25 is 50 minus 21. And of course, 50 minus 21 is going to be 29. All right? So this is 25 is the U.S. medals. The book didn't ask for that, though. They asked for the number of German medals. And there we are. The German medals is going to be 29. All right, not too bad. Same as the earlier ones, with maybe a new little wrinkle. Let's try example 4 in our text. On page 197. All right, again, I'll read through the problem first. Please get your books out and look along page 197, example 4, towards the bottom of the page. All right, talks about bicycles. The Chainwheel Drive Bicycle Company presently manufactures 800 bicycles a month. Each month after this month, the company plans to increase production by 150 bicycles per month until its monthly production reaches 1,700 bicycles. How long will it take the company to reach its production goal? All right. We're currently at 800 bicycles a month. Let me shorthand at least some of this information. Currently, we're producing bicycles at 800 per month. All right, they say each month after this month, the company plans to increase production by 150 bicycles per month until its production reaches 1,700 bicycles. All right, so what I'm going to do is create an expression or an equation involving the number of months needed. So I'm going to say let x, our book says n, let me keep consistent with the textbook's variables. So this is example 4 on page 197. I accidentally erased it. That looks kind of sloppy. Hang on. Example 4 on page 197. I'm going to let n equal the number of months needed to increase production to the 1,700 level, which is what the book specifies. All right, so if we're starting at 800 per month, and we're adding 150 for each month to the production level, I'll say then that 800 plus 150 times n, that's 150 bicycles per month times the number of months, has to equal a 1,700. That's the target production level. All right, once you set these up, really the equations that they give us to wrestle with aren't really that nasty if you think about it. I think the hard part here is setting up the equation, starting out at 800, adding 150 bikes per month, right, until your target production level of 1,700 is reached. So I can solve this now for n very easily, subtracting 800 from both sides. I'll get 900 on the right, and of course the 800s cancel on the left. So n, dividing both sides by 150 then, the 150s cancel on the left, and I'm left with n equals 900 over 150 equals 6. And remember, n is the number of months, so we're going to need 6 months. Okay? All right, I want to do 2 more, and they're kind of similar to the one we just did in example 4. In particular, example 5 on page 198, next page over. All right. The book really has this in a new subsection. It talks about solving application problems involving money, but I think once we look at this problem, we'll agree it's really equivalent to the last problem. Example 5, page 198, grub problem. Part of Kim Martello's lawn was destroyed by grubs. She decided to purchase new sod to lay down. The cost of the sod is 45 cents per square foot, plus a delivery charge of $59. Right? If the total cost of delivery plus the sod was $284, how many square feet of sod was delivered? All right. Let's see. The cost of the sod itself is 45 cents per square foot. So I'll call that $0.45. All right, and I'll symbolize square feet like so. All right, the delivery charge, the flat rate delivery charge for any number of sods is going to be $59 per delivery, right? All right, now we have to have an equation. If the total cost of delivery plus the sod was $284, how many square feet of sod was delivered? All right, first I'm going to invoke a let statement. Let x equal, well, I'm looking for the number of square feet of sod delivered. So they'll say the number of square feet of sod delivered. Number of square feet of sod delivered. All right. All right, so now we need to set up an equation. We want the total cost to be equal to $284. All right, so what I can do is say, well, the cost of the sod, well, it's 0.45 per square feet times x feet, or x square feet, I should say. So I'll say 0.45x, the cost of the sod, plus the delivery charge was $59, has to equal $284. All right, now this equation's got a decimal in it. We can handle that pretty easily, I think. I'll first subtract 59 from both sides. So 284 minus 59 is going to be 225. And we'll probably go to a calculator with this one. And since I have to divide by a decimal, with a calculator should be no problem. The 0.45s cancel on the left, and I'll get 225 divided by 0.45 is 500. So we really should label our answers here. X equals 500. 500 what? Well, remember, x is the number of square feet. So I'll say 500 square feet of sod to put units on our final answer. Okay? Example 5. All right, last one, example 6. Gotta get another screen, hang on. All right, this one, another worked out example in our textbook, example 6, on page, it's really crosses 2 pages, 188, 198, and 199. All right, let me read through it briefly. It's right on the bottom of page 198. Photo printer. Example 6. Elsie Newman is going to purchase a photo printer to print pictures from her digital camera. She is considering an HP printer and a Lexmark printer. The HP printer costs $419, and the cost for the ink and paper is 14 cents per photo. Let me write that down. I'll say the HP printer, well, it costs $419 to start, and the cost for the ink and paper is 14 cents per photo. So I'll write that as $0.14 per photo. All right. Now we're given information about another printer, the other printer that she's considering. The Lexmark printer costs $2.99, and the cost for ink and paper is 18 cents per photo. And let me write that down. We've got the Lexmark printer. It's cheaper investment to start with, but it costs more per photo to produce. Instead of 14 cents here, it's 18 cents, or $0.18 per photo. All right, how many photos would need to be printed for the total cost of printers, ink, and paper to be the same? All right, so I'll make a let statement here. Let n equal the number of photos printed by each of these printers, and they want to know when the cost is going to be the same. At what production output, at what N value, does the total cost of the HP equal the total cost of the Lexmark? All right, well, the Hewlett-Packard starts out at $4.19. Right? And to that, we add 14 cents for each photo we print. All right, so that's on the left-hand side, we've got the cost, total cost of the HP. All right, similarly, on the right-hand side, we'll say, well, we want these to be the same, right? We want the HP cost to equal the Lexmark cost. All right, so I'll say the Lexmark is $2.99 initial investment plus 18 cents per photo, or 0.18 times N. All right, so there is our equation, and it's got a decimal in it, but we should be able to solve this without too much trouble, I think. All right, I would probably subtract $2.99 from both sides. All right, that'll give me a constant over on the left-hand side. And if I subtract 0.14 N from both sides, I'll get a multiple of N, or my N term, on the right-hand side. So 419 minus 299, well, of course, that's going to be 120 on the left. These cancel out. These also cancel out, and 0.18 N minus 0.14 N equals 0.04 N, is it not? All right, one more step, really. I'll divide both sides by 0.04. And of course, I'll use a calculator for this. 0.04 cancels on the left, on the right. So N on the right equals 120 over 0.04, it turns out, is 3,000. 3,000 photos. When we print 3,000 photos, the cost of the Lexmark and the HP printer are the same. Okay? All right, so this concludes section 3.2, solving applications problems. Thank you.